All right, the recording is on, and so welcome one and all to the inaugural Hot Electronic Seminar Talk of the Fall 2018 edition. And my name is Chris Kapulki, and I'm today's host. You're in for quite a treat because we're going to have a 1-hour talk followed by a 30-minute discussion. It's our first talk after the summer break, and so I'm gonna just briefly go over the basics before I introduce our today's speaker. Okay, so we are recording the talk just in case you haven't noticed. And so what that means is that we will ask the speaker afterwards whether we can pause the recording, and if the speaker agrees, we're gonna do it. And so while we encourage you to ask questions and make comments during and after the talk, please keep in mind that if you ask a question that embarrasses you, it will be included in the online posting, and so millions of viewers that watch our talks every day will see that. Okay, but if you're not afraid to ask questions, regardless of those ramifications, which we once again encourage, I would say that the best way to do it is simply to unmute your microphone and ask the question. So what is it called? Zoom has all those nice features with raising hand and so on and so forth. Don't use any of those. Just unmute your microphone and ask the question. All right, so that's how it's going to work. And so now I will introduce the speaker. The speaker will give a 1-hour talk. Please feel free to interrupt them. And then we're going to clap for the speaker. Then we're going to talk for 30 minutes. And then we're going to clap again. And then we're going to meet in a week from now. So keep in mind that usually we meet on alternating weeks, but there will be another talk next week. And then we're going to have a 2-week break. Okay, now that I'm done with all that, I want to say it's a pleasure to introduce Andy Pitts from the University of Cambridge, who's visiting us from the future since his slides say September 2019. So these are some theorems that haven't yet been proven, I'm assuming, and he will talk about axiomatizing cubical sets models of univalent foundations. Andy, take it from here, please.
Yes. Oh, thank you for noticing that mistake, which I'm afraid escaped me. I'm sure there will be many others. So I should also say that I don't think I'm 100% in control of this technology. So forgive me in advance if I don't respond to you. But I would encourage you to try and interrupt me with questions if you have any as you go along. Okay, so, and hopefully you can see my slides. I can see them. This talk, actually, I was doing my research on this, so I noticed that the last talk you had back in the spring, in May, was by Thierry Coquand, and you could say, in some sense, that this is very much following in the same line. So I'm going to give you my take, I suppose, on some of the things that Thierry was talking about. And it's joint work, as it says on the title slide, with my student Ian Orton, with Dan Lecarte and Bach Spitters, and uses lots of other people's works, particularly Thierry and his co-workers, on whose shoulders I'm standing and hopefully not treading on their feet. Okay, and I thought I'd begin by seeing if I can change the slides. There we are, yes, okay. Just with a few sort of general remarks about my own personal motivation for the material I'm going to be presenting to you. So we're going to be looking at models of univalent type theory. And one might ask, why bother with that? Why not just get in there and start doing univalent foundations? And my answer, my personal answer would be, I think, two things. I find the concept of univalence, so it's a sort of extensionality principle for universe, is quite fascinating. And I would like to understand it better and its relationship to other foundational concepts and axioms, and how it can be formulated in different ways. The other motivation for me is to do with higher inductive types, where I think I would like to see in the long run, and maybe even in the short term, their entry into theorem provers based on dependent types in a way that facilitates their use by users. I'm thinking here in the way that the calculus of constructions really took off when it became the calculus of inductive constructions and was provided with things like dependent pattern matching and so on. It became a very usable and addictive thing. And I would like the same thing to happen with higher inductive types, because there are lots of infelicities, let's say, when dealing with notions involving quotients, for example, in existing theorem provers, where hits may help. So this talk is really going to be about the first point and not at all about the second, but I would say in the long run probably that the second point is the most important one, really. And I should say also that neither of these motivations really has much to do with applications to algebraic topology. Important though that topic is, it's not one that personally motivates me. Okay, so what I want from this kind of work is, first of all, I would like to have simpler proofs that universes are univalent in the existing instances that we know of. I would also, in doing that, hope that we will discover, and indeed this has come to be true, that we'll discover new instances, new models, and as I mentioned, hopefully also by looking at what happens in the models, get a better understanding of higher inductive types. So that's what I'd like. How can one approach the existing models? Well, of course, you can. Most of these models, as I'm sure you know, have to do with presheaf toposes, so categories of set-valued functors of various kinds. And of course, you can construct some of the models and describe what's going on in them by just doing direct calculations with presheaves. And with a bit of work, that's maybe not too bad, but there's still, I think, a lot of wood. I mean, the wood being possible worlds and all the kind of need to carry them along and reason with them, that stops you seeing sometimes what the trees are. In other words, what the concepts really are. So that can get direct calculations can get quite hard to follow. Very useful and powerful alternative is what you might call categorical algebra. So I'm thinking of model categories in algebraic approach to homotopy theory. And that's a very powerful and well-developed set of techniques that can help us. I personally wish that I was more familiar with some of the work that's been going on there. One thing I think that if I would not criticize it, but say that it's not so good at is that if you're in the business of giving a model of a particular syntactic type theory, where you're going to have things like substitution of expressions, preserving various constructs up to, say, judgmental equality, then the categorical algebra often glosses over issues to do with strictness there. So everything is sort of up to isomorphism, one might say, and doesn't treat those aspects so well. So in this talk, I'm going to take a third approach, which you might say is just an instance of categorical logic. So it turns out to be the case that if you got an elementary topos, and I'll just briefly recall some stuff about that in a moment, and my toposes are always going to come along with a sequence of countably many internal full subtoposes, so universes, if you like, with the subobject classifier omega sitting in the smallest one. One can give, as I going to tell you in this talk some elementary axioms for an interval-like object. So an object I equipped with two global sections, and some sub-object of proposition, so sub-object of omega, which are going to play the role of propositions against which one can fill in a can-style notion of fibrancy. And the name of the game is to try and work out some hopefully elementary axioms for this kind of structure that suffice to construct, for example, the model of univalence in this paper of Cohen-Coquand-Huber and Mortberg. So from now on, I'm going to refer to those four as CCHM because I can't be bothered to pronounce all their names in one go. Okay, so they have a splendid paper, now a few years old, Cubical Type Theory, Constructive Interpretation of the Univalence Axiom. And that uses the category with family semantics of Martin-Löf Type Theory in a particular category with families associated to a particular presheaf topos. So it's presheaves on box, where box is the Lauvier theory of De Morgan algebras. So what we want to do is to try and abstract away from that particular presheaf topos to toposes in general and see what it is about that particular presheaf topos that we're using in order to construct a model of intensional Martin-Löf type theory with univalent universes. So I hope you know, so an elementary topos, it's a Cartesian closed category with a sub-object classifier, and I'll always assume with natural number object as well. And we know from the last century, as it were, that there's a very close correspondence between instances of that kind of categorical algebra and theories in extensional, impredicative, higher order intuitionistic predicate calculus. Okay. So that's not exactly the logic that we need to use here. We're going to be using a form of extensional Martin-Löf type theory. So if you've got an elementary topos and it's got this sequence of internal full subtoposes, then you can certainly construct a category with families out of it and hence get an interpretation of some form of extensional Martin-Löf type theory. So on this slide, I'm just reminding you in rough terms what that looks like. So the contexts of the type theory are going to get interpreted as objects in the topos. Types in some context, so these would be types of size n, meaning in universe n, as it were. They'll get interpreted as morphisms from the object gamma into this little universe object Sn. And then the terms of such types are going to be sections of the corresponding display that's given to you as part of saying that Sn is an internal full subtopos. And then the judgment that two terms are equal of some type is going to be modeled by their interpretations being equal morphisms in the topos. And when you do that, you get a model of extensional type theory. So you have identity types given by the diagonal on Cartesian products. So that's all well and good, but of course that's in itself not going to give you a model of univalence because of the extensional identity types being, as it were, too thin. So we have to look for something where we can get more intentional models of identity within that kind of setting. And one great way of doing that is to assume that you've got some kind of interval object in the topos and take the notion of identity to mean a path in using that interval object as the codomain of some morphism or more generally internally some function on that interval. So we're going to start with a topos with those universes equipped with some object with a couple of global sections, and we'll think of this as the interval and the cohybrant sub-object of propositions. And one can make a model of Martin-Löf type theory with universes that turn out to be univalent basically by building a new category with families out of the existing one that models extensional type theory. And this looks like the following. So the contexts get interpreted still as the objects of the topos, but now the families in this new CWF are families in the old sense, equipped with some kind of vibration structure. And for the CCHM model there, I'll very imaginatively call them CCHM vibration structures, and I'll just review in a moment what those are. So we get a new notion of family, so the old notion of family equipped with some kind of extra structure, and then the elements of such a family are just going to be elements of the underlying family, capital A. And by positing some axioms about the interval and cofibrancy, it will turn out then that this CWF gives us an interpretation of Martin-Löf type theory now with intentional identity types and with universes that are univalent with respect to those identity types. Okay, so let me just recall what a CCHM vibration structure is. And from now on, I'm going to kind of be describing things without being very precise about what the language of type theory is that I'm using, but using the language of type theory to describe what's going on in this topos E. Okay, so what's a CCHM vibration? So we've got this interval I, so we have a path functor. So I'll write that with this P of gamma. So that's just the exponential gamma to the I. Okay, so the type of functions from I into gamma. So a path in gamma is just a function from I to gamma. And we'll need an extension relation for partial functions whose domain of definition is classified by something in this given collection of so-called cofibrant propositions. So if I've got internally an element of cof, so that's going to give me a particular subterminal. Okay, and if I have a function from that subterminal into gamma, so f is a partial function, or a partial element, if you like, of gamma, whose domain of definition is cofibrant, is coming from cof. We need to consider the relation of that extending to a total element. So I'll write that just with this diagonal up arrow. So it's just a proof of that is just a proof of this universal quantified statement that f maps every proof of phi to this element x in gamma. Okay, so then using extension, we can say what a composition structure is for a family of types. So let's fix one of our little universes in the topos. So S is one of these SNs, and look at a path in S. So that's an interval indexed family of types in the universe S. So a composition structure for such a family of types is going to be something that, given a partial path through the family of types whose codomain, whose domain of definition is cofibrant, if we can lift at that path at the beginning, 0, to some total element A in the family over 0, then we have, if we have a composition structure, a way of lifting to get a total element at the end of the path. So if you can fill at 0 this partial path which has cofibrant domain of definition, then you can fill at 1. And then a vibration for a family of types over some object gamma is just going to be something which, whenever you have a path in gamma, okay, so composing with A, that's going to be giving us a path of types in S, and the vibration structure is going to give you a composition structure for each such path P. So what you could do, right, is work out concretely for the cubical, the presheaf topos of cubical sets, what all that means in terms of presheaves and families of presheaves. And of course, if you look at the original paper, then you won't see this definition. You'll see a more explicit definition in terms of presheaves. And I think it's good to have both, but I think, honestly speaking, I didn't fully appreciate the nature and simplicity maybe of the original definition until seeing it in this form in the internal language. And so the internal language is good for in that respect. Okay, so some simple properties of the interval and the set of cofibrant propositions that allow you to prove some closure properties of this notion of fibration structure. So what we'd like to do is to show that this CWF that we're constructing, where the new family notion is family in the old sense plus CCHM fibration structure, we want that to have sigma types and pi types and identity types and so on. And there are some simple enough properties of the interval and cofibrancy that enable you to prove such things, and the proofs can be given sort of inside this type theory as an internal language, and don't look too bad. And I'm not going to dwell on that at all, because we want to now consider a much harder question of how do we get universes of classifying, if you like, CCHM fibrations, and why are those universes univalent? So it turns out then that you can construct these universes using the so-called tininess of the interval. So this is, I have to say, by way of warning, that the notion of tiny is used in two slightly different ways. I'm using it in one particular way here. Goes back to Bill Levere's work in synthetic differential geometry. So if you're in a Cartesian closed category, you'd say an object, I will say an object is tiny if the functor exponentiation to the I has a right adjoint. I mean, it has a left adjoint, right, product with I, and the exponential is by definition the right adjoint to product with I. You wouldn't normally expect the object then to be such that exponentiation has a further right adjoint. But if it does, we'll say I is tiny. So in that case, you're going to have a natural bijection from morphisms from gamma to the I into delta. They're going to correspond naturally to morphisms into the value of this right adjoint. And I'll write the right adjoint using this square root sign for reasons that I can explain offline. But it's just some symbol as far as we're concerned. The only slight nuance here is that we are dealing with this topos that comes along with a sequence of universes, and we definitely do want the right adjoint to the path functor. This is the path functor to the I. We want that to the right adjoint to respect the size that we have through the universes. So if delta is a global section of some element of Sn, then the right adjoint should also be in Sn. Okay, now we definitely have this in cubical sets, and actually in lots of presheaf toposes, because cubical sets is presheaves on a little category box, right? And box has finite products. It's a Levere theory for De Morgan algebras. So it has a terminal object and it has binary products. Okay, and that's one thing. And the other thing is that the interval object in the topos that we're talking about is representable. It's representable on some object in box that I'll write as I here instead of bold I. Okay, and representable functors in presheaf categories on little categories with finite products, they're all tiny. And that's pretty easy to see, right? Because the path functor, the exponentiate to the I, right? So that's isomorphic to, I mean, if you look at the functor from box to box, which is product with the object I, okay, so pre-composition with that functor, so that's what upper star is doing, is giving you a functor from here to here. And of course, pre-composition with any functor has left and right adjoints given by can extension, right? The left adjoint we know exists, it's going to be product with I, but now we've also got a right adjoint, right can extension, and that's going to give us the square root functor in this case. And actually, if you look at the right can extension formula, it also tells you why size would be preserved in this way. Okay. But that's not particularly specific to cubical sets, right? I mean, if we've got, but on the other hand, it is using the fact that we've got a little category with finite products there, and of course, not all of the examples we might be interested in, specifically simplicial sets, would necessarily allow you to argue like that. Okay, but we are in a situation where the interval is tiny. Okay, and once the interval is tiny, then you can use that in a pretty elementary way to construct a classifier for CCHM fibrations. Okay, so you remember we got families over gamma in this new sense are families in the old sense with a fibration structure. So script fn, right? It's a functor, functorial in the context gamma. Okay, and if your interval is tiny, then this functor turns out to be representable. So there's a particular object. So this is going to be our universe, and it has a fibration. It has a family E, which has a fibration structure on it, and that's generic in the sense that if you've got any other object and a family over it equipped with a fibration structure, then there's actually not just some, but a unique classifier from gamma into UN, so that when you reindex E along this morphism and you reindex the generic fibration structure, you get back the original A and alpha. So that's, I think, is an observation, at least for the specific case of a presheaf topos of Thierry and Christian Sattler. And the proof that we give in this paper that came out this summer is, we might say, sort of an elementary way of seeing that. And the proof of the theorem is sufficiently easy that I'm not going to do very many proofs in this talk, but I thought I would just do this one, just to indicate how things go. So it's a bit of straightforward diagram chasing, really. Starting from the fact that we know that if you've got a family with a fibration structure, so an A with an alpha, what is the alpha actually? Well, I gave you the definition, but what it boils down to is that, so A is going from gamma to S, okay? And what alpha does is to fit into this square here. So you've got the path functor on A, so that's turning paths in gamma into paths of types in S. And then this is assigning comprehension structures, composition structures on such families of types. And A has a fibration structure alpha, just in case this composite factors through the display of the universe. So this, if you like, this S twiddles is just displaying the types in S as a sum. Okay, so this morphism here factors into two things. If the squares are going to commute, the first thing has to be the composite, and the second thing is exactly the same as saying that you have a fibration structure for capital A. So once you see that, then it's kind of pretty, to use a technical term, bleeding obvious what to do, because we have an adjunction, right? So I can flip that square over the adjunction. Okay, so I've transposed over the adjunction. So here's A, here's the transpose of composition. Composition goes from P of S to S. So when I transpose it, I get from something from S into the right adjoint on S. Here I've got the displayed universe with the right adjoint functor applied, and here I've got the transpose of that. So this arrow commutes. So now we're going to take a pullback in this place here. Okay, so we do that, and U is going to be the universe that we're after, and pi 1 actually is going to be the generic family for it. It's a family of things in the universe S. Okay. So we take this pullback, and obviously there's going to be a morphism there because the square commutes, and that's going to be the classifier, the morphism into U that's classifying the original fibration alpha, and it does, it does agree with A. So the only thing left is that we've got to see that this family over U does have a fibration structure, and that's reindexed by this to alpha. And why is that? Well, you just have to look at pi 2 here, right? So if we flip back over the adjunction, right, now we've got this diagram, and here we're going with the transpose of pi 2 into here. Remember, S is just the display of associated with this universe. So that pi2 necessarily factors into two things, and the first thing has to be this composite if the square is going to commute, and the second thing then is exactly, by definition, a fibration structure for pi1. So we get a fibration given by pi1 and epsilon, and the fact that the upper triangle commutes is telling us exactly that when you reindex along the classifier for phi, you're going to get back alpha from E. And this triangle here is telling us that you get back capital A from E. And that's really all there is to it. And the fact that the name of phi is unique with this property just comes from the usual uniqueness property of a pullback. So it's a very elementary argument to construct the fibration classifier, which is nice. Okay, so we have universes classifying the new notion of family, this notion of CCHM fibration. And of course, we want those universes to be closed under the various type forming operations that we're interested in, sigma and pi and identity types and so on. So it turns out this is where one has to, obviously, so far we've assumed that we have a tiny interval. Now we need to assume some more things about the interval. And cofibrancy. And it turns out that if you assign, so that's a sort of weak kind of minimum operation on the interval. And if cofibrant propositions have some pretty straightforward things, so false should be cofibrant. And if you take disjunction with the endpoint assertion that some element of the interval is equal to 0 or is equal to 1. So if you start with something that's cofibrant and you do a disjunction with I equals 0, then that should be cofibrant, and similarly for I equals 1. So those are not very strong conditions to ask of a collection of propositions, but they're enough to get pi types and sigma types, and to get a propositional identity type out of the path types. Okay, so I'm not going to prove that, okay, because what we still have to do is to see why, having got this universe of classifying fibrations with these nice closure properties, why is it univalent with respect to the propositional identity types given by paths? Okay, so that's summed up by the next theorem, okay, which I'm going to have to unpack slowly. Okay, so this is we're going to introduce two extra axioms, one of which is pretty straightforward, and we'll just say that cofibrant proposition should be closed under quantifying over the interval. Okay, and another axiom which I'll talk about in a moment, which I'll call the isomorphism extension axiom. And the theorem says then that if you're in a situation where you have those properties, then it's possible to construct a term of this type. So what I've got here, you probably recognize it, it's just one of the various different ways of characterizing univalence. Okay, so this is saying for the universe UN that this type of equivalences of something in the universe with a given thing U is a contractible type. So let me just do some definitions here in case you're not familiar with my notation. Right, so, but is contractible, usual definition, so basically saying there exists a unique thing. The twiddles here is the path type, so x twiddles x prime is to say that there's a path, so a function from the interval into A, if our path is in A, which begins at x and ends at x prime. Okay, so that's going to be our propositional identity type in the model that we're constructing. Ext, on the other hand, is by notation for saying that you have the ability to extend any cofibrant partial element. So as a type, it's for all cofibrant propositions, for all functions from them. So this is saying for all partial elements whose domain of definition are cofibrant, there should exist some total thing which extends F. Okay, so this is the type that we saw a few slides ago. And I've got two notions of equals going along here. There's the usual notion of equivalence, right, which is here I've given it in sort of what I might say Vygotsky form. So this is saying there is some function from A to B with contractible fibers. Okay, obviously there are other ways that you could formulate that which are equivalent. On the other hand, the notion of equals here appearing in the isomorphism extension axiom is just the back in the extensional type theory, just isomorphism. Okay, so that A is isomorphic to B. There are functions from A to B and B to A, which up to the extensional notion of equality are giving you mutual inverses. Okay, so we just get rid of those definitions for a moment. So the theorem is saying that we can prove univalence for the universe by proving that this type is inhabited. So that's modulo the fact that we now know that UN is closed under various type forming operations like pi and sigma and propositional identity types, then this is equivalent to asserting univalence. Okay, and that's going to follow from the axioms we've already got, plus this closure of cofibrancy under universal quantification over things in the interval, and this. And I just want to spend a little bit of time on this isomorphism extension axiom. So this is not something that you'd see in the original paper by the foursome CCHM, but it's sort of lurking there implicitly. And maybe one of the good things about this axiomatic approach is to put one's finger on something. And again, this is something which is to do with strictness properties. So again, you don't really see this, I think, so clearly if you just work with model categories and everything up to isomorphism. At some point, right, I mean, when you're proving univalence, you've got to actually, from an equivalence, manufacture equivalence between A and B, let's say, an actual path that starts at A and finishes at B, not starts at something isomorphic in the extensional sense to A and finishes at something isomorphic, but actually starts at A and finishes at B. And this extension axiom is the thing that allows us to actually do that. What does it say? It's probably easier just to see it diagrammatically. So what it's saying is the following. You know, I've got my universe of things of size n, and I've got some family in it over some context gamma, and I have a part of that family delta. So I have a mono here, which is cofibrant. So this is going to be a mono that's classified by cof rather than just by omega. And this is a universe, okay, so when you've got two morphisms, you can look at the displayed family of types and ask whether or not they're isomorphic. So I have a family. When I restrict it to a cofibrant sub thing of the context, I can see that it's isomorphic to some family B. So I have something which becomes isomorphic to B on a cofibrant part. And what the having an element of this type, so having an IEA, tells us is that I can then find in some way, so the A prime would be IEA applied to the data, some way of changing A into A prime up to isomorphism, so that when you restrict A prime, you actually get B on the nose up to equality rather than up to isomorphism. Okay. So the extension axiom for isomorphisms is saying that I have a cofibrant thing which is isomorphic when restricted to a given thing, then I can change the total thing up to isomorphism to make the restricted thing actually be equal to what I was interested in. Now, of course, it's all very well postulating that axiom, but it wouldn't be much point in doing it if it weren't true in the places that you're interested in. So in the cubical sets presheaf topos, this is definitely satisfied, right? And it's satisfied actually in pretty much any presheaf topos, as long as your notion of cofibrancy is sitting inside. So, well, let me read you this. What it's saying is that if I have some presheaf topos, not necessarily cubical sets, right, So I've got cough is some sub-object of omega. Omega, if you remember in presheaves, is just the thing that at each stage gives you the sieves on the object X in the little category C. So if I'm at stage X, and if I have a cofibrant proposition, that's going to be a particular sieve, right? So it's a subset of the morphisms into X. And if my cofibrant things are such that those are always decidable subsets of C over X, then I can prove this isomorphism extension property, or we can. I mean, this is something that Ian Orton observed. So actually, if you're in a classical meta theory, right, then where this being a decidable subset, in other words, either a given morphism into X is in S or it's not in S. So if you've got the law of excluded middle, that's no condition at all. So classically, every presheaf topos has this property. So this isn't. You should think of this isomorphism extension axiom as being a very, very, very anodyne kind of thing. It's classically kind of true but does need the law of excluded middle to apparently to do it. I think it's either Christian Zattler or Andrew Swan who has an observation about the extent to which, if you've got this, you must have the law of excluded middle. And I can't recall which of those to prove something that they did. Okay, so that's a theorem, and I am not going to prove you that theorem here and now, because actually its proof is pretty non-trivial, I would say. And to prove it, you have to sort of combine.
Can I interrupt and ask a question about the previous slide?
Absolutely, Emily, yeah.
Actually, two questions. So the first is this isomorphism extension axiom. It looks like some sort of isofibration property to me. Is this saying that the universal CCHM fibration over the universe is an isofibration in the sense of lifting isomorphisms?
I think it's saying something like that, but it's not really specifically to do with CCHM fibrations at all, right? Because so this is just, you see, I mean, this is a property just of cough, okay? And cough is just some sub-object of omega. So what you do with it later is to do obviously with CCHM fibrations, but actually, in fact, there are other notions of fibration that people have considered, and this same extension axiom gets used. But I agree, I'm sure in terms of fibrant, the theory of fibrations and Cloven and fibrations and so on, it's probably saying something that people can tell me they already know. Yeah.
Could you say also what, or remind me again, what it means for Cove to be closed under for all I and I?
Well, in terms of that you're more familiar with, probably. And so if you think that if we look at the monos in the topos that are classified by, so Cough contains the true proposition. I didn't say that, but it's a consequence of the axioms. So we've got a global section of Cough, and we can look at monos that come by pullback from Cough, right? So we have a little class of monomorphisms which are cofibrant. So that's really what I meant by this being cofibrant. It's the pullback of true in Cough. So to answer your question, then being closed under for all I is just to say that cofibrant monos are closed under exponentiation by I. So I have a cofibrant mono and I raise it to the power I, it's still cofibrant. So that's equivalent to the internal statement that just says, if I have internally, if I have a function from I into cough phi, and if I look at the proposition for all I phi of I, that's in cough. So that's so. Is that okay? Yeah.
Yes, thanks.
Okay, cool. Thank you. Yeah, so so this is, to my mind, not a particularly easy theorem, actually. So it uses things like the gluing construct. So that's coming straight out of the original paper, but then you can express that nicely in terms of the internal language. some stuff that Ian and I did, the sort of whole kind of equivalence extension property, which is lurking in the background here, is really, you should read about it in Christian Sattler's paper. And the stuff to do with why U exists in the first place. So that there are two things, right, in the conclusion of the theorem that's coming out of these axioms. One is that this actually is univalent, so that's this statement here. And the other thing is, of course, it's no good it being univalent if UN isn't, as it were, an object in the type theory that you're constructing. So you need the universe itself to be fibrant over one. So that if you didn't have that, obviously then UN wouldn't be an element of UN plus one. So you wouldn't have a sequence of universes anyway. But of course, you want it to be fibrant in the first place, so that it's a type in the CWF, as it were. So there are two things to prove there: that UN is itself fibrant, and that the generic vibration is giving you something that's univalent. And they both come out of sort of equivalence extension, which is itself coming out of gluing. But there are some pretty tricky, I would say, nuances to that. You use the isomorphism extension property to, the first version of gluing is sort of up to isomorphism, and then you strictify it using isomorphism extension to get it working up to equality. But in doing that, you lose control over exactly what the fibration structure is on the thing that you're getting out of the extension axiom. You know that there is one because you can transfer fibration structures along equivalences and along isomorphisms. But the thing that you get might not agree, as it were, with the equivalence at each end of something that you started with. So in the middle of this proof, you have to prove a kind of so-called realignment statement about fibrations, which is, again, possible to do, and I certainly find it easier to do it working inside the type theory than to do it, say, diagram chasing style. So I'm not going to say anything more about this proof. And what I am going to do is summarize where we are, okay, and then move into the last part of this talk, which is about modal type theory. So what we've got, right, just to summarize, is that I started with an elementary topos with sequence of internal full subtoposes containing the propositions in the smallest one. Got an interval, and we had to assume some things about it. I didn't mention all of them, but here I've tried to mention all of them. So we want the endpoints of the interval to be distinct. Without that, you'd have a degenerate model anyway. And also the fact that 0 doesn't equal 1, it gets used in one or two places in the development anyway. The notion of cofibrancy should contain the endpoint assertions be closed under disjunction and universal quantification over I, and satisfy this isomorphism extension property. Then, through what I've indicated, we can construct a new CWF with a sequence of universes in it, which are univalent, which do have pi types, sigma types, and propositional identity types, and various other inductive types like W types and so on. I've been saying propositional identity type all the time because that's what you get, but you can correct that. I think Andrew Swan observed how to do that in this particular setting, but you do need a little extra axiom to do that. So we didn't, in our assumptions about Koch, we had some sort of disjunctive character and some basic things that should be cofibrant and closure under for all. If you assume that Koch is a dominance, in other words, closure under dependent conjunction, then you can fix up judgmental identity types out of the propositional ones in a certain way. And you need, yeah. Yeah.
Could I ask about the tininess of the interval?
Yeah.
Is it tiny in the internal type theory, or is it?
Well, You're anticipating my next slide, right? Okay, so just put that question on hold and you'll see it answered. Okay. Right, so what we would like to do, right, several things we'd like to do, but what I would like to do is if you look at the formal development of what I said, sort of done in a kind of type theory matching that topos, we apparently have been using the subobject classifier, right? And that's an impredicative universe of propositions. But that impredicativity really isn't something that's playing a serious role here. So it would be nice to remove that and just formalize everything within intentional Martin-Löf type theory with some axioms, maybe function extensionality or UIP, uniqueness of identity proofs, and so on and so forth. So that's what we're going to do next, except, to answer your question, we can't, right? And we can't because there's a serious problem. And this problem sort of stopped Ian and I for a year or so from completing this program. And we couldn't see any way around it. And the problem, I can crystallize it now that we know that tininess is being used to construct the universe. The problem is that tininess is not an internal property. So if I in Martin-Löf type theory write down my interval object is tiny, I'm going to in effect write down that it's tiny in each fiber, fiber wise it's tiny, or internally it is. And that's just not true, right? Well, it's true only when the interval is trivial, okay? And I can show you that pretty straightforwardly, really. See, tininess says that there's a bijection between Hom sets, right? Morphisms from gamma to the I to delta are naturally in bijection with morphisms from gamma to delta, to the right adjoint at delta. What it does not say, right, is that can be internalized to an isomorphism of types between the function type here and the function type here. And you can see why not, right? Because, I mean, suppose we had that natural isomorphism, right? We can do a little calculation, right? So the right adjoint at delta, well, that's the same, that's isomorphic, right, to the, x to the 1 is always isomorphic to x, right? So I've got functions from 1 to this object. That's just isomorphic to the object, right? But if I've got that internal right adjoint, then I can flip it over, right? And it's morphism, it's functions from 1 to the I to delta. And of course, 1 to the I is just isomorphic to 1, right? So this whole thing is just 1 arrows delta, which is delta. So if you string that together, and that argument is completely natural in delta, right? We've got a natural isomorphism between the identity functor and the right adjoint, right? So if I now take left adjoints, I'm going to get a natural isomorphism between the identity and the path functor, right? The identity is isomorphic to the 1, so if you think about it, that can only happen because 1 is isomorphic to the interval. So we would degenerate to an interval where the endpoints are the same, and hence everything is equal to everything. And that's not going to give us, obviously, an interesting model. So tininess is inherently a global, not a local property. So what we do in the paper in FSCD this summer is to bite the bullet and do a bit of modal type theory. So we're taking the system I would personally, as it were, prefer to be working in, intentional Martin-Löf type theory with UIP, uniqueness of identity proofs, and Martin-Hoffman style quotient type. So that gives you function extensionality and disjunction for mere proposition. So these are the basic kind of things that you need in order to do the kind of constructions I've been talking about. But we want to postulate also that the interval is tiny, and we've got to do that in a way that restricts things so we have to be able to speak of a type's global elements, as it were, rather than just all its internal elements. So we do that by having a modality for expressing that distinction between global and local. And I think some of you, watching this talk are infinitely more able and aware of all the multifarious work on modal type theory that has been and that there is. So there's a lot going on. We kind of used bits of it. I think we mostly used stuff, and here, of course, Dan Nakata was a great help to us. We sucked out a bit of Mike Schulman's really nice paper on spatial type theory for real cohesive hot. So we don't need full spatial type theory. We just need a little bit of it. But our thinking was very much influenced by what's in that paper from 2017. And for some reason, this type theory is going to be called crisp type theory. So you think of somehow the assumptions about things being global will be crisp assumptions, and the local ones will be like cohesive assumptions. And you can formulate things in a sort of Fenning et al. Style dual context, if you like, which we do like, I guess. So I'll say a bit more about that in a moment. So crisp type theory, you can formulate it with judgments look like this. There's a sort of context divided into two bits, and the left-hand bit, we're making assumptions, we're introducing variables of various types, but these are crisp variables, if you like, so standing for unknown global elements of the type, whereas the right-hand part of the context is cohesive variables, okay? So standing, as it were, for internal elements. And the basic sort of hygiene here is that all the types in the left-hand context and all the terms that you substitute for variables that are declared there can only depend on variables that are declared in that left-hand bit, in the crisp bit, okay? So I'm very strongly a believer in when devising whatever kind of type theory that you should have some intended model in mind to guide you. So here, I mean, we're thinking, you know, about the cubical sets model, presheaf model, and that's going to model crisp type theory in the following way, right? I mean, we have a functor on the presheaf category, I'll call it flat, okay, but that's just takes a presheaf to the constant presheaf on the set of global sections of A. So that's a limit preserving idempotent comonad, because I guess because the category of De Morgan algebra, free De Morgan algebras is got finite products, it has a terminal object, so it's connected, and that's enough to see that this constant global sections endofunctor is got this stuff. And then you can use that to interpret this judgment, so that the left-hand bit delta will just be an object in the cubical sets topos. Gamma will be a family that depends not on delta, but on the flat of delta. And then A, this type, will be a family that depends on the comprehension of gamma in that context, flat delta. And then A, this term, will be an element of that family, capital A. And then one can proceed to interpret the stuff. I could give you some rules. I thought on this slide I'd just flash a few, but I think since I see the time is getting on quickly, let me just say that the one thing that we really do need is we need the ability to form pi types over crisp variables, over things coming out of the left-hand part of the context, so that the rules I highlighted in red here are giving us that. Okay, and that gets, we don't actually in fact use a modality explicitly at all, but we do use this pi type of so-called crisp functions depending crisply on their variable. And actually, in fact, what we do is to develop everything in an experimental implementation of Agda called Agda Flat that Andrea Vezzozzi very kindly provided for us. So it's a sort of subset of the kind of thing that he and Neutz and De Vries have been doing. You know, they have a modal type theory account of parametricity and various other things, and we're just using a subset of that Andrea has kindly provided for us. It's really nice in some ways because it's a very anodyne, small extension of Agda. I'll just show you a little bit of what it looks like, because whilst it's very nice, I also want to point out that it's also not so nice. And I underlined experimental here for a good reason. So the thing is that you're adding this kind of flat modality, or this distinction between crisp and cohesive, into the whole of Agda as it is. And in particular, Agda allows you to do all this cool stuff with dependent pattern matching. And that maybe has consequences that are not so clear to begin with. So I'll just show you a little bit of what the thing looks like. So on this slide, what I'm trying to do is get a helper function that you need all the time. It's a version of congruence for, not for ordinary functions of a cohesive variable, but for functions of a crisp variable. So, but if you look here, this is sort of an example of a split context. So the A and the X and the Y are sort of in the delta bit, and the B and the F are kind of in the gamma bit. So that's my sort of delta gamma, as it were. And in that context, I'm trying to construct an element of this function type. If I have a proof that X equals Y, do I have a proof that Fx equals Fy? So that's the congruence property for functions of this type. But this, is, you see, is a crisp function type, not a cohesive function type, because of the double colon there. Okay. So if you do use Agda flat, unfortunately, you can't write double colon. You have to write this crap here, but that's just, never mind that. Now, Agda flat won't accept that as a definition because you're trying to define a function here which is a variable ranging over this type, but it's a cohesive variable. And it turns out that semantically that's not correct, but I think it's maybe not so immediately obvious why that's true. So if you type this into Agda flat, it won't type check it. It'll say that this doesn't type check, and it'll give you this helpful error message that tells you, what at least tells you that probably you need to think about the type of the REFL there that's in red. And indeed, if you change to a crisp function, so taking, as it were, a global proof that X equals Y, then you can show that this crisp function preserves that. Then Agda flat is happy, and we'll say that that's a well-formed definition. I don't know whether we're happy or not, because what it's showing is that the ability to do pattern matching and nested patterns allows a lot of expressivity with respect to so this is something which, if you look in Mike Schulman's paper, would be proved, but by using the further right adjoint to flat, what that's called, I forget what it's called, but if you're into that sort of thing, you know what I mean. Here we don't need any further right adjoint to the modality. We can just define the thing as is, but using pattern matching. And actually, we don't need the modality at all, but you can define it if you want to as an inductive data type. So flat of A is sort of the generic thing that has a crisp function into it from A. And using pattern matching, you can prove that type forming operation flat on types from Sn to Sn has all sorts of extremely nice conservation properties, which is good, but maybe a bit worrying from the point of view. So experimental in the sense that we maybe don't have a full hold over what Andrea has given us in this. But it's really useful though. So let me, and then rapidly coming to a close here. So how do you use crisp type theory? So we can now postulate tininess in a way that's correct, right? So writing it in Agda flat, I'm now saying that I have an operation which doesn't take in an internal element of the universe, but a global one, and gives you a global one. And here I'm writing down that you have the exponential, the adjoint transpose operations, and that they do give you a bijection, and that they are natural. And this is enough stuff to tell you that you've got a right adjoint at the global level to the path functor. And then you can use that to turn into a piece of Agda flat, the diagram chase that I gave you as the proof of the construction of the univalent universes UN, and actually prove that they're vibrant and univalent. So let me try and wrap up. So one thing that's going on here, I think, is that so we've axiomatized some stuff. Maybe what wasn't immediately apparent, but is really true, is that the fact that path types were given by full exponentials is actually really very making life a lot easier here, because the exponential functor is fiber-wise, and so there's a lot of stuff that you can state internally about path types, which wouldn't be so easy if you were dealing with a path functor that was only global or was given maybe by some linear style exponential to a kind of tensor product. So I'm thinking here that, you know, in simplicial sets, this kind of approach isn't so easy. And so we internalized into type theoretic language a lot of the constructions, but the thing that we couldn't do was internalize the construction of the universe, and so that was inherently global, whether you use tininess or not. And this modal type theory came to our rescue to be able to express things nicely. So that's one thing. So it's helped me understand the original cubical sets model, but of course one would hope that then, now you've got these axioms, maybe you can satisfy them in other places. And we're beginning to see that in ways. So, I mean, for example, Taichi Uemura, forgive me if I pronounce his name incorrectly, has some stuff about the effective topos and independence of having an impredicative univalent universe. And that's using some of our approach, but with an elementary topos rather than a Grothendieck topos. That's quite nice. And there are also things where, you know, like with the guarded cubical type theory, where you work in a presheaf topos, not the original box, but sort of box cross, say omega for time steps in the topos of trees, etc., etc. So that's all well and good. But I would say it's still, you know, it simplified things, but there's still in the end some delicate and hard work. And actually we found using a theorem prover, so Agda flat in our case, actually really invaluable. I don't think I could have be sure that we got things right without it. So highly recommended. And if you want to look at our codes, you can see some of it at that place there. But in the end, I'm not a satisfied person, because I still think I don't understand why giving models of univalence, and I mean sort of non-trivial ones where you say, you know, it's not truncated potentially at any level, or you've got a wide class of homotopy types that are going to be faithfully represented in there. Why that's so hard to do, I don't know. And I would really like to see radically different ways of doing that. I mean, and one way that one might do that is to ditch the whole can filling thing in terms of something else, maybe some notion of path composition. And I've thought about that quite a lot, and I almost have a univalent model based on path composition using some of the ideas I've described, but unfortunately at the moment not quite. And the other thing is that one wonders why presheaf toposes are so predominant. Why not sheaf toposes? I mean, I grew up in sort of the world of, you know, using sheaf theory to force various things to either be true or not true in the context of constructive predicate calculus and so on. And one would maybe like to use a little bit of Grothendieck topology or something in order to make models. So this is the kind of thing that Thierry, I think, was talking about in the talk that you had last in this series. And there are issues there in sheaf toposes with getting universes to give you sufficiently strict modeling of type theories. You may end up where the code of a pi type codes something only up to isomorphism rather than up to equality. And I've been doing some work recently with Thierry Coquand, which maybe we'll get around that, but that's another story. So I'll finish there and recommend this paper of the four of us if you want to see more details, and take any questions if there are any. Thank you.
All right, thank you very much. I'll now unmute everyone's microphone so that we can clap. All right.
Cohen-Coquand-Huber-Mo, they have minus. Yeah. Because they have the wave theory of De Morgan algebras, which is.
Hang on 1 second. Hang on. I muted everyone's microphone. And now, if you want to ask a question, please do so. I heard someone speak, so I just want to make sure that if you're speaking, please unmute your microphone first. Wow, I scared
Well,
someone.
you stopped that in its tracks.
No, please, say what you were saying.
And they were asking each other questions, not asking me a question.
And we should be like teachers in like elementary school. Yes, tell everyone. We all want to know what you're talking about. Okay, so we'll wait for a bit. We have 20 minutes, so we can make it really obvious.
Okay, I'll ask a question. Can you hear me?
Yes, Dan, I can.
Yes, great, good. Can you turn to slide 14?
Mm-hmm. That one?
No, sorry, let me go on.
That one.
That's strange. No, it's not that one either. Maybe it was before 14. What? Something happened. No, it was definitely later than that. I must have got the number wrong.
I think Dan will be doing that for 20 minutes now.
This is the one. Sorry, it was 15.
Yeah.
Okay.
Right. Cool.
Can you just explain this interpretation again, this model you want?
Yeah, okay.
In particular,
So
just to one point in particular, you're writing curly E of some arguments. I just don't quite understand.
oh yeah, sorry, that's that. I didn't. Maybe I flashed through that too quickly. So the notation I use for categories with families, right, is that when I write like here, for example, right, that's a family over this object. Let me go back. Let me refresh my notation for you. I got it here. Hang on. Yeah. So I see your confusion. I think I actually removed the notation slide at some point and didn't put it back. Sorry about that. So good. Let me explain that notation again. So if you've got a category of the families, right, you have an underlying category, and then over each object you have a set of families, right? So if delta is an object in the topos, right, then flat of delta will be an object in the topos, and I can consider a family over it. If you like, you can think of that as just E sliced over B delta, but I want distinguished pullback. So instead of just using slice categories, I'm using this equivalent category of families equivalent to the slice category. So gamma isn't an object, it's a family over this object. So that's the constant presheaf on the global elements of delta. And then since that gamma is a family over this object, I want to stick the two things together. So that's my notation for the context extension, right? So that's like this is the total object of the family gamma. Okay, so that's now an object in the topos, and I have a family A over that. So that's like exactly saying that A is something in context of gamma, delta and gamma, and I'm interpreting this split context by sort of being flat delta comma gamma, as it were. And then this is just my notation for the elements of the family A. Happens to be a family over this object. So I apologize. I think I excised the notation for CWFs when preparing these slides and then forgot that I'd done it. So
right. Yeah, that's good.
Thank you for asking that. Yeah. I should say, by the way, that actually Agda flat, right, isn't internally formulated at all in terms of this dual context formalization. It uses that other way of doing modal type theory, which I think also Frank Fenning suggested, where your context has both sorts of flavors of variable assumption in it in any order, So it has, sort of, as it were, double colons and single colons all mixed up together in some order. And then you use a process of subtracting out stuff in some of the rules. So instead of always rigidly dividing in two, you have an operation on context for subtracting out some cohesive part of the context when formulating the rules. So Andrea's little formalization of what the type theory is that he's implementing in Agda Flat wouldn't look like these kind of rules, but would look in that kind of subtracted form, which I don't think probably has had a categorical semantics job done on it. I mean, there are lots of things that need doing in this area. Semantics of crisp type theory is certainly one of them. Yeah.
So in the problem with universes for sheaf toposes,
yes,
you mentioned the law of excluded middle, but it seemed like you were using it mostly in external things. Is it enough to have it for crisp, or I guess, I don't know what you would call it, they're discrete objects? Or?
I think there's two things being mixed up there, right? So there's an issue with universes in sheaf toposes, but that's not so much to do with classical versus non-classical logic. So I mean, even if you're working in classical meta theory, suppose we're absolutely satisfied to be in ZFC, right? And I want to do a Hofmann-Streicher style universe, but not in a presheaf topos, but in a sheaf topos, right? So I think Thomas Streicher observes, I think in his paper on universes in toposes, that you can do the Hofmann-Streicher thing on the presheaf topos and then apply sheafification, and you do get some kind of universe object. The problem is that sheafification is going to mess up things like the universe giving you exactly up to equality, you know. I'll end up having code, say, for pi types, where if I decode the code of a pi type, I don't get exactly the pi type, but I get something isomorphic to it. So if you don't mind that, and maybe you shouldn't mind that, then maybe there isn't a problem. But if you actually want to model, you know, universes in as they are in, you know, Koch or Agda or whatever, where you know, well, actually they're done Russell style, aren't they? But even if you did them Tarski style, which would be semantically a bit easier, you'd still want the code of pi of something to be the pi of the codes, as it were. And that's not so easy to see how to do by using this sheafification. So we have a suggestion, a way of that seems to be giving you something that's working quite nicely, replacing sheafification with something weaker. So it's like, roughly speaking, just using the existence part of the sheaf condition and not the uniqueness part. But that's an oversimplification, and that's coming to you in another talk sometime.
All right, we have a bit more time, so please don't be shy.
Could you go back to the statement of the theorem, the theorem that had a difficult proof?
Yes.
Right.
Yeah.
So, assuming that what I'm going to ask makes sense, is it sensible to ask whether your IEA axiom is stable under operations you might perform on the underlying topos? So, for instance, I'm thinking of, you know, this result by Mike Schulman on if you take inverse diagrams on some model of homotopy type theory, you know, you still get univalent universes.
Yeah.
So something like, you know, taking E-valued inverse diagrams, would that still satisfy your conditions, thereby also giving more models of univalence?
I mean, I don't know the answer to your question, but my guess is definitely yes. And I think what I should say about this is that whilst we are using this axiom, it's a convenient way of formulating something, but it does remain the case that it's, if I put this back, this axiom is true in the cases we're interested in for a different sort of reason to do with this decidability thing happening in your meta theory. So a more satisfactory thing would be to directly capture in crisp type theory, right? In other words, in the modal type theory, something which says something about the more like your cofibrant things are somehow externally decidable sub-objects. So this IEA is a consequence of this, but this, in a sense, is this thing in the red box here is perhaps more important. But I don't myself see, maybe it's just, I think, probably a failure on my part, how to formalize this in the kind of language that we've got at the moment. Whereas I do see, you know, as it were, how to formalize in the language we've got this thing. So, so I guess what I'm saying is that whilst this is a fun thing to do, it's maybe not the most fundamental thing or the last word on the subject. And one should think, as it were, especially if you want to, as you say, do the same kind of thing in other places by maybe, you know, doing some you know, presheaf on, you know, taking an internal category and doing presheaf on that in some place that you already know works. It may be that this is this kind of thing is the easier thing to think about than that. Yeah. Okay.
Thank you.
All right.
I mean, by the way, just to say, I mean, if you don't care about constructivity, right, then this condition is always true. So that would sort of just be saying that you might as well take off to be omega, and that would correspond just to, you know, to the situation where you just take all monos to be cofibrant, which we see in various, you know, in like Szynski and things. Yeah.
All right, we'll wait a second for another question. But since time is getting closer and closer to 1, maybe we won't wait indefinitely. So if you have a question, now would be a really good time to ask it. And okay, that's the final call for questions. Okay, if there are no further questions, in that case, I'll unmute everyone's microphone again, and we're gonna thank Andy again.
Okay,
all right.
Anyway, so then we're having now and then. So the idea is if you have a morphism, then
okay, so I guess Jana's explaining something will be our final memory of this meeting. Okay, but I just have one final announcement. We're going to meet next week, not in 2 weeks. So starting next week, we're going to meet on alternating Thursdays, but keep in mind that there will be a meeting next week, and we'll have Dimitris Tsimentsis speak about first-order logic with isomorphism. And that's it. So thank you very much, and see you next week.